Ammonia is a weak base, and if ammonia reacts with water, water is going to function as a Bronsted-Lowry acid. So water is going to donate a proton to ammonia, and ammonia is going to accept a proton, so it's going to be a Bronsted-Lowry base. So a lone pair of electrons in the nitrogen pick up this proton, which leaves these electrons behind on the oxygen. And if you protonate ammonia, you form ammonium, the ammonium ion, which is NH4+. So let's show those electrons. So these electrons, this lone pair of electrons here on the nitrogen, pick up this proton and form this bond right here. So we form NH4+, and these electrons in blue come off onto the oxygen. So the oxygen had two lone pairs of electrons around it, and the electrons in blue are now around it, which give it a -1 formal charge here. So we form the ammonium ion, NH4+, and the hydroxide ion, OH-. So if ammonia functioned as a Bronsted-Lowry base, over here would be the conjugate acid, right? So ammonium is the conjugate acid to NH3. And water functioned as a Bronsted-Lowry acid, so over here would be the conjugate base, the hydroxide anion. So instead of using ammonia, let's just do a generic base. So here I have B written. So some generic base reacts with water, takes a proton from water to form BH+, and if you take a proton away from H2O, you would form OH-. So once this comes to equilibrium, we could write an equilibrium expression. So we're going to write Kb here. So instead of Ka, we're now writing Kb because we're talking about a base. And Kb can be called, you can call this the base ionization constant. So let me write base ionization constant here. Or you could call this the base dissociation constant. So base dissociation constant. And when you're writing an equilibrium expression, remember, it's the concentration of your products over your reactants. So over here we have the concentration of BH+ times the concentration of OH-, and that's all going to be over the concentration of your reactants, and we leave out water, so we have only the concentration of our generic base B. So you can think about Kb the same way we thought about Ka. Right? The higher the value for Kb, the stronger the base, because the more of your products you're going to make here. All right, so let me go ahead and write that. So the stronger the base, the larger the value for Kb. So let's talk about two weak bases here. So we've already mentioned ammonia, and we're going to compare ammonia to aniline. So NH3 is ammonia, and the Kb for ammonia is 1.8 times 10 to the -5. And aniline is C6H5NH2. And notice it has a lower value for the Kb. 4.3 times 10 to the -10 is a much smaller number, a much smaller value than 1.8 times 10 to the -5. So ammonia has a higher value for the Kb, and therefore it's a stronger base than aniline. So once again, both of them are weak bases, but ammonia is the stronger of the two. Remember when we talked about Ka, we also talked about pKa, and so we're going to do the same thing here. We've talked about Kb, and so now let's talk about calculating the pKb. So the pKb is equal to the negative log of the Kb. So let's say we wanted to find the pKb for ammonia. All we'd have to do is plug in the Kb value, and so the pKb would be equal to the negative log of 1.8 times 10 to the -5. And so let's get out the calculator here and do the problem. Negative log of 1.8 times 10 to the -5. And so we get 4.74 here. So the pKb for ammonia is 4.74. And you could do the same calculation for aniline and plug in this Kb, and you would get a pKb of 9.37. So comparing two weak bases, ammonia and aniline, ammonia is the stronger of the two because it has a higher value for the Kb. And notice that the pKb is a lower value. So once again, analogous to what we talked about for pKa. So next, we'll do a calculation for a solution of ammonia. Our problem asks us to calculate the pH of a 0.500 molar solution of aqueous ammonia. So we have ammonia in water, so we have NH3 plus H2O. And ammonia is going to accept a proton from water and turn into NH4 plus ammonium. And if water loses a proton, H2O turns into OH minus. So let's go ahead and write our initial concentration here. So for ammonia, we have 0.500 molar. So we write 0.500 molar here. And we're pretending like nothing has happened. So the concentration of our products is 0. So nothing's happened yet. So the concentration of ammonium is 0. And the concentration of hydroxide is also 0. Next, let's think about the change. Right, so since ammonia, since NH3 turns into NH4+, the concentration of ammonia that's lost is the same concentration as ammonium that is gained. And if we represent that concentration using X, so if we lose a certain concentration of ammonia, that's the same concentration of ammonium that we gain. So this would be plus X over here for ammonium. And it'd be the same thing for hydroxide. So this would be a plus X here for the hydroxide anion. Therefore, at equilibrium, for ammonia, the concentration of ammonia at equilibrium, we would have 0.500 minus X. For ammonium, we would have X, and for hydroxide, we would also have X. So next we write our equilibrium expression. So we write Kb here is equal to the concentration of our product, so that's NH4+, so I write NH4+ here, times the concentration of hydroxide, and that's all over the concentration of ammonia, We leave water out, so this is all over the concentration of ammonia here. So let's plug in what we know. So at equilibrium, the concentration of ammonium is X, So let's write in an X here for the concentration of ammonium. And it's the same thing for the concentration of hydroxide. So for hydroxide, the concentration at equilibrium is also X. So we write an X right here. This is all over the concentration of ammonia, and that would be the concentration of ammonia at equilibrium is 0.500 minus X. So we put in 0.500 minus X here. This is all equal to the base ionization constant for ammonia. And let's go back up to our table above to remind ourselves of what it is here, So ammonia has a Kb of 1.8 times 10 to the negative 5. So we're going to plug that value in for Kb here. So this is equal to 1.8 times 10 to the negative 5. And once again, we're going to assume that X is much, much smaller than 0.500 molar, because that makes our life easy for the math. We don't have to do the quadratic formula if we do that. And if we make this assumption, then 0.500 minus X, if X is extremely small, this is pretty much the same thing as 0.500. So we're going to leave that out. Let's rewrite what we have here. We have 1.8 times 10 to the negative 5 is equal to, this would be X squared over 0.500. So all we have to do now is solve for X. And so we would have X squared is equal to, 1.8 times 10 to the negative 5. We have to multiply that by 0.5, and we would get 9.0 times 10 to the negative 6. So next, we just take the square root of 9.0 times 10 to the negative 6 to solve for X. And let's go ahead and do that. So let's get out the calculator here, and let's take the square root of 9.0 times 10 to the negative 6. And so we get 0.003. So let's go ahead and write X is equal to 0.00030. And remember what X refers to. Let's go back up here. Let's think about what X is talking about. X is talking about a concentration And notice we have an X here for our concentration of hydroxide anions. And that's what's going to allow us to eventually get the pH, which is what the question asked for. So X is equal to the concentration of hydroxide anions. So this would be molar, right? This is our concentration of hydroxide anions. And our goal is once again to find the pH of our solution. So first we could find the pOH. So that's one way to do it. The pOH is equal to the negative log of the concentration of hydroxide ions. So we could go ahead and take the negative log of 0.0030 to calculate the pOH of our solution. So let's do that on our calculator. So negative log of 0.0030 is equal to 2.52. So the pOH is equal to 2.52. And then to find the pH, all we have to do is subtract from 14, because pH plus pOH is equal to 14. And I believe in a previous video I forgot to put these zeros here if you're concerned about significant figures. Right? So you plug in your pOH into here, so your pH plus 2.52 is equal to 14.00. And so you just solve for pH. So pH is equal to 14 minus 2.52, which is 11.48. So finally, we've calculated the pH of our solution of ammonia.